Okay, so we want to talk about how we describe or how we can describe circular motion. Okay, yeah. So we want to talk about how we can describe circular motion. And when when we talk about circular motion, basically we are talking about an object moving in a circle. For example, if a car is going around a roundabout, or if a planet is going around the sun, that is a kind of circular motion we're talking about. But there's also another kind of circular motion which happens when an object is spinning on an axis. For example, the tire of a car, if it's spinning on its axis, that's another type of circular motion which we're interested in. Also, for example, for the Earth to do this business of night and day, it has to spin on its axis. So basically, those are the two kinds of circular motions we're talking about. So the circular motion we're interested in here is one which consists of an object moving in a circular path, and also an object might not necessarily move in a circular path, but if it's spinning on an axis, then that's what you're interested in. So we want to find out how we describe this kind of motion. So there'll be some new terms which you have to come to know how to define and also how to use. The first term you're going to come across is angular displacement. The other one is angular velocity, and another one is angular acceleration. Now, when we were talking about motion in a straight line, we described the motion in a straight line in terms of displacement, in terms of velocity, and in terms of acceleration. It happens that also when we are actually talking about motion of an object in a circular path, or if an object is rotating or spinning, we can also describe such motion in similar terms. And we're talking about angular displacement, angular velocity, and angular acceleration. So we are going to try to see what these are. Now, there are many activities which make modern life possible, and one of those things which has made modern life possible is the application of circular motion. Our cars, bicycles, motorcycles, they depend on the wheels of the bicycle or the wheels of the car or the wheels of the motor bicycle to spin. That's what makes our modern transport work so well. Also, for example, you've got trains which carry heavy things, and trucks, they need to have wheels. So basically, when it comes to a wheel spinning on an axle, that is a type of circular motion. So us moving from point A to point B, previously it used to take weeks and months for people to do that, but now because we have got cars and we have got bicycles and stuff like that, it takes you a lot less time. So that is one obvious application of circular motion in cars, in vehicles, trains, bicycles. So we use circular motion there. So cars depend on tires, and those tires need to turn. Okay. The other things is, for example, we were having this whole problem of traffic management. So one way to manage your traffic is a roundabout. So if you somewhere on a road or a bunch of roads which are very busy, if you put a roundabout there, then somehow you can put streetlights also. That is also going to help. So with a roundabout, you can make sure that a lot of cars can use the same road without having congestion. Okay. Apart from cars, which make life quite easy, and also roundabouts, cars and roads, life on Earth was not going to be possible if the Earth didn't move in a circle, and also if the Earth did not spin. The Earth moves around the sun in a time period of 365 quarter days. So it takes the Earth 1 year to go around the sun. And that's how basically people know how many years they've been living on Earth. If you tell me you're 17 years old, or you're 19 years old, or you're 16 years old, it basically means that since you're born, the Earth has gone around the sun that same number of times. So the Earth goes around the sun, but apart from the Earth going around the sun, the Earth also spins on its axis. So the spinning of the Earth on its axis is what makes night and day. And if the Earth was not spinning, then one side of the Earth would be completely daylight, and the other side of the Earth would be darkness. And I don't think life would exist like that. The other bit basically means that maybe people would have difficulty sleeping, and the other people would be sleeping for a long time. I'm not sure, but I think it would be difficult to live in such a world. Okay. So the Earth spinning on its axis makes it possible for us to have day and night. But also the Earth going around the sun, it also makes it possible for us to enjoy all these seasons which we have. Right now we're in winter, very soon winter will be over, will be summer and stuff like that. So all these things is possible because the Earth is going around the sun, and the whole process repeats itself. So basically, without the Earth going around the sun, and also without the Earth being able to spin on its axis as it does, life would not be possible. Okay. Then the other things which go around the sun, for example, the moon also has got its own uses. At night, when the sun is gone, is on the other side of the planet, the moon gives us light so that you can see where you're going, at least. And also you can continue with things. Life can continue because you have a bit of sunlight, so you have a bit of light which is being provided by the moon. And the moon goes around the Earth a certain number of times. Other things apart from the moon, which is the natural satellite, we also have got artificial satellites. For example, DSTV satellites. And that's what makes it possible for you to watch television in your living room. You can watch all your movies or your TV shows, whether it's football or all these other kind of sports. You can watch them because of satellite TV. And those satellites are continuously moving around the Earth. Okay. So satellites make possible for you to have satellite TV, but they also make it possible for you to have internet. Okay. Previously, before we had optic fiber cables, the internet came from satellite. It was a bit expensive, but that was the only way. Right now, at least, because of fiber cables, it's possible for people to have cheaper internet. And yeah, but there are other places where satellites are the only way for you to get internet. So basically, if you want to speak to the outside world, or you want to see what's happening in other countries, you most likely will need a satellite TV. Okay. Also, a lot of computers still use hard drives, and these hard drives have got tape inside them, magnetic tape. So this magnetic tape spins, and it's this spinning which makes it possible for your hard drive to read data from your computer, to read data from your hard drive, and also to store data. So our computers right now, where we are, most computers have got a hard disk inside, and it has got a part which spins and reads data. So the computer age and information, your WhatsApp and all these things, without hard disks, things wouldn't have been possible. It would have been impossible for us to store as much information as we store these days. Of course, there's changes which are being made to how hard drives are being made. These days, you've got solid state drives which don't require any part to spin. So yeah, there are new ways of accessing data from computers, but previously using a hard drive which could spin was the only way to do it. And I think there is still a lot of computers which still use hard drives which spin. Circular motion is also used in hospitals to find out what kind of disease you're sick of. For example, you have machines called centrifuges which rotate and spin blood samples or samples from patients so that they can find out what technicians and biochemists can find out what kind of disease a person has. But you also have got other kind of machines called magnetic resonance imaging scanning machines, these machines also have got parts which spin, so that they can make an image, quickly make an image of your body, whether it's your chest or it's your head or whichever part, so that doctors can see inside your body without opening it to find out exactly what's going on with you. So there is still a lot of uses where circular motion is being used. Apart from computers and also hospitals, you also have use for circular motion in kitchens. You have got blenders and mixers. They help us make food nicely, good food. For example, if you want a milkshake, you put your stuff in a blender, then you turn on the blender, then it's going to mix up all these things, blend them, and at the end of the day, you're going to have your milkshake. So that also exploits circular motion. So basically, these are some of the applications which have made life very convenient, and they are all as a result of an application of circular motion. There might be other uses which people can come up with, but all that depends on a very good understanding of what we mean by circular motion and studying it. Okay, and that's basically what we're going to do in this course, in this lesson here. So the first thing we're going to do is, how do we describe distance in terms of circular motion? Now, when it comes to circular motion, we define distance basically in terms of angles, not distance in meters. But the distance in meters, as we're going to see, is related to the distance which is in terms of angles. Okay? So the example we're going to use is an example of a car which is going around a roundabout, or a car which is moving in a circular path which has got a certain length. So this circular path has got a length S, and also it has got the radius r. So you have a car which is moving in a circle. The circle in which this car is moving has radius r, and this particular circle has got a length S. If you kind of cut the circle and find out how long it was, that would be your S. But this particular circle we are concerned about here has got length S and also radius r. Now, there is a connection between the length of this circular path S and the radius. The length of a circular path, that is what we call the circumference. From your mathematics, grade 11 mathematics, I think, the circumference of a circle, which we're calling S here, is equals to 2 pi r. So this is the first connection we get here. So the first thing we're seeing here is that if you have a particular circle, a circle of a certain length, and you know the radius, there is a connection between the length of the circle, which is S, and the radius of the circle, which is r. And that connection is S is equals to 2 pi r. So here, there is this r. R is the radius of the circle. Then S is the length or the circumference of the circle. The question is, what is this bit here? The 2 pi. Now, this 2 pi which you are seeing here is basically what is referred to as, it's an angle. Okay? 2 pi is an angle. 2 pi is an angle. So, from this expression, what you see is that somehow, if you want to find out the length of a circle, how long a circle is, you need to multiply by this 2 pi, then r. If you multiply by 2 pi r, then you are going to find what the length of the whole circle is. This 2 pi is an angle, and we know that 2 pi is equivalent to, if some people know, 2 pi is equivalent to 180 degrees. So 2 pi is equivalent to 180 degrees. 360 degrees. 360 degrees is an angle. Okay? If 360 degrees is an angle, then 2 pi is also an angle. But 2 pi has got units which are not degrees. 2 pi is measured in what's referred to as radians. It is this 2 pi here which is referred to as angular displacement. The 2 pi we are seeing here is an angle referred to as angular displacement. So what we are trying to say here is that it is possible for you to measure distance in terms of angles. You can measure a distance in terms of angle. For example, 20 degrees, 30 degrees, 45 degrees, 90 degrees, 60 degrees, 180 degrees, or 270 degrees, or 360 degrees. You can measure distance in terms of angles. And when you're measuring distance in terms of angles, the distance you measure in terms of an angle, that's what is referred to as angular displacement. So this 2 pi here, you're seeing here, this 2 pi is actually the angular displacement, and the angular displacement is denoted as theta. So generally, if you know what the angle is, if you know the angle through which an object moves, and you know the radius of the circle through which it's moving through, if you multiply theta, which is the angular displacement, multiplied by the radius, then you are going to get how much distance in meters that particular object or that particular car has moved, or that particular person has moved in meters. So this relationship, what we have here, when we replace this 2 pi, which is the angular displacement, when we replace it with theta, what we end up with is a relationship S is equals to theta multiplied by r. Theta is the angle through which an object moves, r is the radius of the circular track through which the object is moving, and S is the actual distance in meters that particular object has moved. Are we clear? With this relationship, this is a starting point. The distance of a circle, or the distance through which a person moves, an object moves in a circular path, is equals to theta, which is the angular displacement, multiplied by r, which is the radius of that circular path. This theta is measured in radians, and 2 pi radians is equivalent to 360 degrees. So from this formula which you have here, S is equals to theta r, we can make theta the subject of the formula. When you make theta the subject of the formula, we end up with theta is equals to S divided by r. S here is the arc length. The arc length, or the actual length in meters you move in a circular path, divided by the radius of that circular path. If you do this, theta is equals to S divided by r. This gives you your angular displacement. So theta is equals to S over r. That's your angular displacement. So your angular displacement is measured in radians. Your S is your arc length, is measured in meters. Your radius is measured in meters. So when you divide, you end up having your angular displacement, which is going to be measured in radians. The short form for radians is the rad. And 2 pi radians is equals to 360 degrees, like I've mentioned before. The other way, so you have got, right now you have got 2 ways of measuring units of measuring angular displacement. You can measure angular displacement in terms of radians. You can also measure angular displacement in terms of degrees, but it's also possible for you to measure angular displacement in terms of revolutions. How many times you have gone around a circle. So if you go around a circle once, that is 1 revolution. That 1 revolution is equivalent to 360 degrees, and that is also equivalent to 2 pi radians. Normally, when it comes to calculations or whatever stuff you have to do, which involve angular motion or angular displacement and other things, you have to express your angular displacement in radians. So if you're given your angular displacement in revolutions or in degrees, you need to change your angular displacement in radians so that you can actually do the things you need to do. Are we clear with this? Is it clear to everyone what we mean by angular displacement?
Yes, it is clear, but they are on the meters. Is it always converted into centimeter or the distance has to be always in meters? How should the distance be?
Usually we convert it into meters, but sometimes because you're dividing, for example, like in the example we have, it's pointless converting into meters because you're dividing the distances. So usually we convert into meters, but sometimes you might not convert into meters. You can just divide if you've got the units are the same. Okay, for example, if you look at example number 1, a bob of a pendulum 90 centimeters long swings through a 15 centimeter arc as shown in figure 1. Find the angle theta in radians and in degrees through which it swings. So if you look at what we have, basically the diagram is here. So you have got a pendulum which has got a length of 90 centimeters, and this bob is swinging through an arc of 15 centimeters, an arc which has got a length of 15 centimeters. So this 15 centimeters is the actual distance which the bob moves, but it's moving in a circular path, as you can see. So the path through which a bob moves is part of a circular track or a circular path. So the length of the pendulum becomes the radius of this circle, like that. So the radius is going to be 90 centimeters, and the actual length, distance through which the bob moves, is 15 centimeters here. So we can find what this is. This angle theta. This theta you're seeing here, this angle you're seeing here, this is the angular displacement. The theta you're seeing here is the angular displacement. What is the distance moved in terms of angles? This theta is the angular displacement. Are we clear on what we mean by angular displacement? Is it clear to everyone? Okay. So the angles, if you measure, say, 45 degrees or stuff, that is the angular displacement you're talking about, through which an object has moved. So in this case, our angular displacement theta is just going to be equal to S over R. That's going to be 15 centimeters, which is the arc length, divided by the length of the pendulum, which is 90 centimeters, which is the radius. So in this case, it's really pointless trying to change into meters. You can do that, but the answer is still going to be the same, because you're going to cancel out whatever units you have. Then you're going to end up with 0.17 radians. This. So this is going to be your angular displacement. Very small, 0.17 radians. So this is the angular displacement in radians. But we know there's a relationship, this relationship here. So you can use this relationship. 360 degrees is equal to 2 pi radians. So you can use this relationship to convert this theta which you have here, to convert it into degrees. So basically you multiply on top, you multiply 360 degrees, at the bottom you divide by 2 pi radians, and you're going to end up with whatever your angle is, theta, in degrees. Are we clear?
Yes. So you're saying that you always change the radius into degrees, you always divide the answer by the angle that you're given in the question.
Sorry? You use this relationship. Use this relationship. 360 degrees is equal to 2 pi radians.
Yes.
This is how the radian is related to the degrees. Or pi is equals to 180 degrees. So if you are changing to... Yes, so if you are changing this into radian, into degrees, this one here, 0.17 radians, you are going to multiply, it's going to be 0.17 radians times 360 degrees divided by 2 pi radians. Then you get your angle in degrees. Yeah. So this 0.17 radians times 360 degrees divided by 2 pi radians. Then that's going to give you an angle in degrees. Are we clear? Yes. So that's how we describe angular distance or angular displacement. So distance in terms of angles. Now, if we have a way of defining distance in terms of angles, sometimes we see the sun. The sun rises in the morning in the east, it goes around the sky and it sets in the west. So basically, the sun, between what we believe is a distance of is a time period of 12 hours from 6 to 18, which is what we believe is 12 hours, the sun covers an angular distance of 180 degrees or pi radians from the morning all the way up to the evening. So you can find out how fast is the sun moving across the sky. So the angle in that case, if you know how fast something is moving around the sky, you know how much distance. So since it starts in the morning all the way up to the afternoon, you can make an estimation, say it's going to be 180 degrees or pi radians. Then that pi radians divided by how much time it takes a particular object to move around the sky. In this case, it's 12 hours. So this 12 hours, you have to change it into seconds. So you can work out how fast, how many degrees per second or whatever it is, the sun is moving around the sky. So basically, that is a way of measuring how fast an object is moving. Okay, so if you divide your angular displacement, if an object is moving in a circular path, then it covers a certain amount of angular displacement. Then you divide that angular displacement by how much time it takes. So the angular displacement divided by how much time it takes something to move around the circular path, then what you end up having is a physical quantity called angular velocity. So this angular velocity measures how fast an object is moving in a circular track, or how fast an object is spinning on its own axis. What looks like W here, it's a Greek letter called omega. So this omega is what we use to denote the angular velocity. The angular velocity is equals to the angular displacement divided by the time it takes to cover the said displacement. We know that the angular displacement is measured in radians and the time is measured in seconds. So radians divided by seconds, you end up having units of rads per second for angular velocity. Like that, rads per second for angular velocity. So this is how one way of defining what is referred to as angular velocity. Are we clear? Angular velocity is how fast the angular displacement, how much angular displacement you are covering per unit time. That's what your angular velocity is. And angular displacement is measured in radians, then the time is measured in seconds, so you end up having units of radians per second. Are we clear? Okay. Now, if an object moves in a circle, whenever an object moves in a circle, like that once, if an object moves once in a circle, then the angular displacement covered is 2 pi radians. If an object moves in a circle once, then the angular displacement covered is 2 pi radians. The time it takes an object to move in a circle, that time is what is referred to as period, and we denote the period as t. So we are now considering a case where an object moves in a circle once. If an object moves in a circle once, the distance or the angular distance or the angular displacement which an object has covered is 2 pi radians. And the time, whatever time it takes this particular object to move in a circle, that time is what is referred to as the period. So what are we trying to do here? So we consider a case where an object moves in a circle. So theta is going to be 2 pi radians, and it's going to take a certain amount of time, capital T, to move in that particular circle. Okay. Now, there is a relationship, another relationship which you come across in physics, and this relationship relates the period, which is the time it takes an object to move in a circle, to something called the frequency. The frequency is basically a measure of how fast you are moving in a circle per second. How many times do you go around a circle in 1 second? That is frequency. So if you go around in a circle once per second, that's fine. So the frequency is 1 hertz. So frequency is a reciprocal of the period. So frequency is equals to 1 over t. So from this relationship, you can see that if it takes you a lot more time to move in a circle, then your frequency reduces. But if you move in a circle faster, then your frequency increases. Okay, so basically frequency measures how many times it takes you to move in a circle. Okay, and it's related to the period. The units of frequency, which is F, frequency is measured in hertz, and basically a hertz is, we are assuming by definition you move once in a circle per second. Now, with what you have with what we have set up, say, let's consider an object which moves in a circle, and it takes a certain amount of time t. So the angular displacement will be 2 pi, and the time it takes that object to move in a circle is going to be t. So we can express our angular velocity omega as theta divided by t. Since the object moves in a circle once, so the angular displacement is going to be 2 pi, and the time it takes to move in that particular circle is going to be capital T. So the angular displacement for 1 revolution is 2 pi, and the amount of time it's going to take is capital T, which is a period. You can rewrite this expression, 2 pi divided by t, you can rewrite it as 2 pi 1 over t. When you do this rewriting of 2 pi over t as 2 pi 1 over t, then you recall from up here that frequency is equal to 1 over t. Therefore, this 1 over t, you can replace this 1 over t with f. So you end up having this. Omega, which is angular velocity, is going to be equals to 2 pi divided by, 2 pi multiplied by the frequency. This is another way of expressing the angular velocity. You can find out what the angular velocity is by multiplying by 2 pi times how many times this particular object is going around a circle per second, which is what is referred to as frequency, which is measured in hertz. Is this clear? Omega is equal to 2 pi f.
Yes, it's clear, sir.
All right. Now, this one here, I think there is a mistake here, because this what we have here, average angular velocity. Average angular velocity is supposed to be what? This is supposed to be written as theta f plus theta I divided by 2. So there is I think there's a problem here. Okay, so I'll need to correct this, but we don't need it right now. Okay, so the other way, apart from measuring angular velocity in terms of radians per second, as you are going to see from example number 2, the angular velocity can also be given in terms of what's known as revolutions per minute. Revolution is basically how many times a particular object is going round a circle per minute. So if you go a certain number of times in a circle per minute, then you can give the speed or the angular velocity in terms of revolutions per minute. Okay, and that's what you're going to, that's another way. That's a common way in which the angular velocity is given. So example number 2, a flywheel turns at 480 revolutions per minute, and this revolutions per minute is denoted as RPM. Compute the angular speed at any point on the wheel and the tangential speed 30 centimeters from the center. So in this case, basically, this 480 revolutions per minute is the angular speed itself. But basically, I think what we're being asked here to do is we want the angular speed or angular velocity in radians per second. So basically, you need to change 480 revolutions per minute into radians per second. And basically, the way you do it is, first of all, you have got here 480 revolutions, 480 RPM. That's going to be equals 480 revolutions per minute. Then for this revolutions per minute, remember, one revolution is equals to 2 pi radians. So you can multiply by 2 pi radians and divide by a revolution. Then also you have to remember that 1 minute is equals to 60 seconds. So you can multiply by a minute and divide by a second like this. So you end up with 480 revolutions here times 2 pi radians per revolution divided by 60 seconds, and you're going to end up with 50.3 radians per second. I think this has to be written more clearly. It's not very clear what's happening, but I will, in the notes after we are done with the lectures, I will need to properly redo this calculation so that you can see exactly how you convert from revolutions per minute to radians per second. So basically, this is what you're going to end up with here. So this is how fast. This is the same as 480 revolutions per minute is equals to 50.3 radians per second. So that's the angular velocity or the angular speed. For this angular velocity or angular speed, you can find out what is the actual speed in meters per second if you are at a particular distance from the center. So in this case, we are being asked to find what is the speed if you are 30 centimeters away from the center of this flywheel. So in that case, if you want the velocity, your velocity v, again, before it is given by this, v is equals to r multiplied by omega. How do you come to this expression v is equals to r multiplied by omega? If you look at what you have here, up here, what we started with here, s is equals to omega, s is equals to theta multiplied by r. So this side, if you divide s by t, then you divide this whole thing, theta r multiplied by, divide by t. So if you divide by t both sides, so this side you're going to end up with s divided by t. That's going to give you the velocity. Then this side you're going to end up with theta r divided by t. You're going to end up with theta divided by t, and theta divided by t is just omega. So you're going to end up with v equals to omega r. Here, omega is theta divided by t. So if you divide both sides of s of this expression, if you divide both sides of this expression, s is equals to theta r divided by t both sides. So this, you end up having v this side, you end up having omega here. Theta divided by t, that's going to give you an omega. So you're going to end up with omega Alright, like that. So basically, that's where this relationship comes in here. So you end up having, you have this. So your velocity in meters per second, which is what is called the tangential velocity, is going to be equals to the radius multiplied by the angular velocity. The radius, in this case, since you already have your angular velocity in radians per second, you need to change your radius in meters. So your this is supposed to be another mistake here. So this is supposed to be 30 centimeters. 30 centimeters is supposed to be equals to 0.3 meters. So you end up having this. So again, another correction. I think I need to go through this thing. So this is going to be 0.3 meters multiplied by this bit here. So you end up having 15.09 meters, which is approximately just 15 meters per second. Like that. Is that clear? On how you find the velocity of a point, if you know the angular velocity and you know how far this particular point is from the center. So the tangential velocity v is equals to r multiplied by omega. Yes, is there a question? Okay, next. I think a similar question, I think. A fan turns at a rate of 900 rpm, which is revolutions per minute. Find its angular speed at any point on one of the fan blades, and B, find the tangential speed of the tip of a blade if the distance from the center of the tip is 20 centimeters. So again, this which we have here, this 900 rpm, this is an angular speed or an angular velocity, but it's given in the revolutions per minute. So basically, if we ask you to find what the angular speed is, we are asking you to give us this same angular speed or velocity, but in radians per second. So again, something which I need to work on here, so that it can, the whole expression, the whole thing you can clearly see how the conversion is being done. So omega is equal to 900 rpm, that is equal to 900 revolutions divided by 1 minute. So this 900 multiplied by 2 pi radians per revolution, then divided by 60, then you end up with 994.2 radians. So this is how fast the fan is rotating, 94.2 radians. With this value of angular speed, then you can also find out what is the actual speed, tangential speed of a point which is located 20 centimeters away. So in that case, we have got this bit here. So the velocity v is equals to r omega. So in that case, your v is going to be equals to your radius. So this is radius in centimeters. You need to change this radius centimeters to meters. So you end up with v is equals to 0.2 meters multiplied by the angular velocity, which is 94.2 radians per second, and you end up having a velocity of 18.8 meters per second. Are we clear? Is it clear? I'll need to redo these conversions. So be on the lookout probably over the weekend for updated notes which clearly show how to do these conversions. So I'll need to redo these conversions so that you can clearly see how you convert from revolutions per minute to radians per second. So I'll update the notes. Right now they're updated because there's something I changed, but I'm still not happy with this the way the conversion is like this. It's not very clear to a student what's happening. Okay, so I'll need to rewrite this properly so that you can clearly see what is it I'm doing and how do you convert from revolutions per minute to radians per second. So basically the point here is, if you are given an angular velocity in the revolutions per minute, you need to change it to radians per second. Is that clear? Yes, if you are given an angular speed in revolutions per minute, that has to be changed into radians per second. Okay. The next, now, we have talked about angular displacement, which is the distance you cover in terms of angles. We have also talked about angular, what's this? We have also talked about angular velocity. Now, there are some objects or there are some bodies which are fine. They have got the same angular, what's this? They've got the same angular velocity. For example, when our planet is going around the sun, okay, when our planet is going around the sun, every time it goes once around the sun, the angular distance it covers is 2 pi radians, because it's one revolution, and that one revolution is equivalent to 1 year. Okay, so every time our planet goes around the sun, that is one revolution. That is the angular displacement, and that angular displacement is 2 pi radians. So one revolution equals to 2 pi radians. Okay, then the amount of time it takes 1 year, which is 365 quarter days. The thing with our planet is that it takes the same amount of time always. There is no year where we say the planet moved faster this time around, or this year the planet was moving slower, or maybe the planet had a puncture in space, then it had to make repairs, that's why it has delayed. No, it doesn't happen. Okay, unless there is some collision or something like that, it doesn't happen. So our planet always takes this, it moves in space around the sun at the same rates. Basically, it moves at constant angular velocity. It moves at the same rate. Okay. The other bit also is, you have to remember that for you to have day and night, the Earth spins on its axis. Now, the spinning of the Earth on its axis as it's moving around the sun also happens at the same speed. So that is also another form of an object which is having the same constant angular speed. But it's not always that an object is going to move at the same angular speed. There are times when it's important that an object moves faster, spins faster. For example, if you're driving a car, then you want to overtake a truck, or you want to, maybe the police in front of you, you might need to slow down. So as you are slowing down, that is a process of making the wheels of your car spin slower. So you apply the brakes and eventually your tires move slower until they come to a stop. But if you're overtaking, of course, you press on the accelerator and the tires of your car will start spinning faster, which means that you're going to cover more distance in a much shorter amount of time. So if an object's angular velocity changes, then that is acceleration. If an object spins faster or slows down as it's spinning, then we're talking about angular acceleration. If an object is moving in a circle, like our planet moves in the circle around the sun, then if our planet starts moving faster, maybe for some, for some whatever particular reason why, then the Earth starts moving faster in space, then we are going to have what is referred to as angular acceleration. Or if the Earth starts spinning faster on its axis, so day and night become very short. So whatever used to be 24 hours is no longer 24 hours, maybe it's now 12 hours. So you've got daylight for 6 hours, you've got night for another 6 hours. So if the planet starts spinning faster, then our 24 hours is going to become smaller. That is what is referred to as angular acceleration. So if the angular velocity of an object moving in a circle or of an object spinning on its own axis changes with time, then we say that that particular object has undergone angular acceleration. And this angular acceleration is basically a measure of how fast the velocity of this particular object is changing with time. So if you know what is the final angular velocity, omega I, then you know what is the initial angular, you know what is the initial angular velocity, then you know how much time it takes for an object to speed up from omega I to omega f. Then you can get the angular acceleration alpha like this. Alpha is equals to omega w, omega f minus omega I divided by t. Omega f is the final angular velocity minus the initial angular velocity divided by the time it takes for this change in speed, angular speed, to happen. This change in angular velocity is measured in radians per second divided by the time, so you end up having your angular acceleration in units of radians per second. Are we clear? So sometimes objects are going to spin faster, or objects are going to slow down as they are spinning. How fast the velocity, the angular velocity is increasing, or how fast the angular velocity is reducing, that is what is referred to as angular acceleration. Are we clear? Yes. Okay. So here's an example. A wheel of 40 centimeters radius rotates on a stationary axle if it is uniformly sped up from rest to a speed of 900 revolutions per minute in a time of 20 seconds. So you have got a wheel which has got the radius of 40 centimeters. Then this wheel was at rest. Then it speeds up to 900 revolutions per minute in 20 seconds. So the question is, what is the constant or the average angular acceleration alpha? So we know that it was at rest. When it was at rest, it was covering 0 revolutions per minute. So the initial angular velocity is 0 revolutions per minute, 0 RPM. Then after 20 seconds, it ends up having 900 RPM. So again, like I've mentioned about RPMs, whenever you've got RPMs, these RPMs have to be converted into radians per second. And again, I've mentioned that I'm not happy with how I wrote things, the conversions, so I will need to rewrite these conversions properly so that you can see how they're being done. But if you bother to do it, so 900 RPM is going to be 900 revolutions divided by 1 minute. Then this 900 revolutions multiplied by 2 pi radians divided by a revolution, because 2 pi radians is equal to 1 revolution. So you multiply by this, then you divide by the 60 seconds, and you're going to end up with 94.2 radians per second. This is the final angular velocity. The initial angular velocity is 0 RPM, and that 0 RPM is just 0 radians per second. So in that case, you have got initial angular velocity, which is 0 radians per second, this bit, 0 radians per second, and you also have your final angular velocity, which is 94.2 radians per second, and this whole thing happens in 20 seconds. So you can work out what is your what is your average angular acceleration. So omega f minus omega I divided by t. So this is going to be 94.2 radians per second minus 0 radians per second divided by 20 seconds. So this bit here, up there, you end up having 94.2 radians per second divided by 20 seconds. You end up having this. Alpha is equals to 4.7 radians per second squared. So this is your angular acceleration. Your angular acceleration is also related to your actual acceleration in straight line, like this. A is equals to R alpha. A is your acceleration in straight line. So now that you've got alpha, which is our 4.7 radians per second squared, you can multiply it by the radius, which is R, which is in mid. We told it's 40 centimeters, but you have to change the centimeters into meters. So you end up having A is equals to 0.4 meters multiplied by 4.7 radians per second, and you're going to end up with an acceleration which is approximately 1.9 meters per second squared. So basically, this is how you get your acceleration A from the angular acceleration alpha. A is equals to the radius multiplied by alpha. So you can see, what you see from what you have done so far is the connection between linear acceleration and angular acceleration. These things are related. A is equals to R alpha. When you talk about the linear velocity, your velocity V here, V is equals to R omega. So you keep on multiplying the rotational part by the radius. If you also look at the displacement, S up here, S is equals to theta R, like that. So this first part here, where especially with the conversions, I think just this evening I need to rewrite these conversions so that I post a version of the notes which shows better conversions, much easier conversions, so that you can follow along, because most often you're going to be given your angular speed in the revolutions per minute, then you need to do the conversions, and basically I need to update the notes just this evening so that you have a much better way of doing things. Any questions with what you have done so far? Yes?
What's the difference between the angular speed and the angular velocity?
It's the same.
The same.
Yes. Yeah. Any other question? Can you speak up? Speak up. Can you repeat the question? Yes. A is acceleration in a straight line. The A is a linear acceleration. When you're moving in a straight line, what is your acceleration? When your velocity changes from u, initial velocity, to final velocity, divided by the time. A is equals to v minus u divided by t. So this is acceleration. A is acceleration in a straight line. Then the alpha is how fast something is rotating. The change in how fast is the change in rotation. So alpha is concerned with how fast the velocity is changing in a circle or when something is spinning. So alpha is angular acceleration of things which are moving in a circle or things which are spinning. When they spin faster or they slow down, that's what alpha is. A is an actual object moving when an object's velocity increases or reduces, but this particular object is moving in a straight line. So for A, an object is moving in a straight line. For alpha, an object is moving in a circle or is spinning. Is that clear? Yes. Any other question? Okay, if there are no other questions, we'll stop here. We'll finish up this thing tomorrow. So we've done halfway, 5 pages. We're left with another 5, so we'll finish it up tomorrow. All right, so see you tomorrow at same time. Yes.
Thank you.
Excuse me, sir.
Yes.
When can we expect the notes?
There are already notes there on Moodle Anga. These ones I'm just updating them. But you already have notes on Moodle. These updated notes, I'm going to do them this evening. So probably check tomorrow morning. You should find something which is latest there.
Okay, thank you, sir.
Yeah. Any other questions? Okay, we're done.